Welcome back to The Explainer. Today, we're embarking on a truly thrilling guided tour through the dense, sometimes kind of intimidating, but absolutely fascinating world of quantum computing. I'm going to be your personal navigator through this incredibly complex landscape, and we're mapping out exactly how this revolutionary technology is poised to upend everything from medicine to global security. We're going to break down that barrier between theoretical physics and actual real-world computer science and chart exactly how this whole thing works right from the ground up. But hey, before we start looking at complex hardware and mind-bending physics, I want to set the stage with an incredible quote. In the acknowledgments of our source text, the author actually grounds us with the wisdom of the 2nd century BCE Tamil poet Aviar. The quote goes, "What one has learned is equivalent to a handful of sand, and what one is yet to learn is as big as the world." It's such a humbling reminder, right? No matter how advanced our science gets, what we currently know is literally just a handful of sand compared to the vast world of the unknown. So if you ever feel a little intimidated by quantum mechanics, just remember that we're all just exploring that handful of sand together. It's the perfect mindset for what we're about to dive into. Okay, let's dive into this. Our foundational map for today's explainer is Venkateswaran Kasirajan's massive text, Fundamentals of Quantum Computing, Theory and Practice. Now, I know what you're thinking. A textbook of this size might look incredibly daunting at first glance. But instead of an impenetrable wall of equations, what we're actually looking at is a brilliantly structured, highly accessible visual guide. If we approach it with that humble, curious mindset we just talked about, this text unlocks the secrets of the quantum realm step by step. So here's our map for today. We'll start with a handful of sand, then look at choosing your quantum path. From there, we'll hit the foundations of the quantum world, followed by the essentials of building the machine, and finally, we'll look at the future of quantum. All right, moving into our first section, choosing your quantum path and tailoring the journey to your background. Here's a little secret about entering this field. You absolutely do not need a PhD in theoretical physics to get started. Our source material does something really brilliant here by laying out entirely different routes through the material based on who you actually are. If you're a university physics student, well, you take the scenic route through the heavy math. We're talking linear vector spaces, tensors, and Dirac's bracket notation, which is basically the standard mathematical language for describing quantum states. But if you're a software developer or a general enthusiast, you get a completely different map. You get to bypass that heavy introductory math and jump straight into Hilbert space and the core principles of quantum mechanics. It just goes to show that this territory can be tailored exactly to your background. Next up, we have the foundations of the quantum world, where we start descending into the quantum realm. Think of this as stepping into a reality that is completely counterintuitive to literally everything we experience in our daily lives. We are officially leaving classical physics behind, folks. We get hit with this rapid-fire sequence of concepts that honestly sound like they belong in a sci-fi movie, but they are intensely, measurably real. We're talking about wave-particle duality, where matter somehow acts like both a solid particle and a radiating wave at the same time. Then we explore quantum tunneling, where particles essentially just phase right through solid walls. No way, right? And we even get into exotic states of matter like anyons and Majorana fermions, particles that uniquely exist only in 2 dimensions. It is a high-energy crash course in how bizarre the universe truly is at the microscopic level. Now, what's really interesting about this is how the author handles the most famous quantum concept of them all, Schrödinger's cat. You know the one. It's the classic thought experiment illustrating a quantum superposition state, where a cat in a box is theoretically both alive and dead until somebody actually opens it up and looks. But check this out. The author actually includes a humorous little warning pulled straight from chapter 3. Do not try this at home. It's just a great little injection of personality into some very heavy physics. Moving right along, we arrive at the essentials, building the machine, where we transition from theory to practice. So the absolutely crucial point here is that eventually we have to leave the realm of abstract thought experiments and actually build something. We have to make that hard pivot into engineering and computer science. So how do we actually build this thing? Well, the roadmap follows a very strict progression. Step 1, we have to figure out the physical material to build our qubits. Step 2, we have to figure out how to wire those incredibly fragile qubits together into functional quantum circuits. And finally, step 3, we have to write completely new software algorithms that will actually run on this brand new hardware. Let's zoom in on that first step for a second. Right now, there isn't just one single way to build a quantum computer. We are witnessing a massive, high-stakes competition between very diverse physical technologies. On one side, we have trapped ion qubits competing against superconducting transmons. It's essentially a technological race balancing pure processing speed against quantum stability. And on top of that, we even have theoretical topological qubits, the anion model, and electron spin in quantum dots. The entire industry is just furiously trying to figure out which of these modalities is going to become the ultimate victorious foundation of quantum computing.
But here's the catch. Almost all of these technologies share one massive engineering hurdle. I absolutely love this question, pulled straight from our source material. How does the dilution fridge cool the qubits? Because to keep these incredibly fragile quantum states from collapsing, they have to be kept impossibly cold. We're talking about extreme, near absolute zero physical conditions. It literally requires massive, highly specialized refrigeration units just to keep a microscopic qubit stable enough to perform a single calculation. It's wild.
So why go through all that trouble? Well, once we have stable circuits, we finally get to the algorithms. And this brilliantly illustrates the incredible world-changing software power these machines are eventually going to unlock. We have Grover's algorithm for unprecedented database searching. We've got Simon's algorithm and quantum phase estimation. Most famously, though, the source material walks through Shor's algorithm, specifically demonstrating the exact quantum circuit required to factor the number 15. Now, factoring numbers might sound simple enough, but scaling Shor's algorithm is literally what threatens to break modern global encryption. Yeah, that is the kind of power we are talking about here.
Finally, we reach our last section, the future of quantum, looking beyond the horizon. Because honestly, despite all this incredible theory and all these super powerful algorithms, we are still facing some massive hurdles before quantum computers become an everyday reality. Just like the early days of classical computers, today's quantum computers make mistakes. They're noisy. So the biggest challenge of our current era is the path to fault-tolerant computing. This requires highly complex quantum error correction. In the text, we explore Shor's 9-qubit code, planar surface codes, and the engineering of protected qubits. Basically, the idea is we have to use multiple physical qubits just to create one stable, error-free logical qubit. It is a monumental mathematical and engineering challenge for sure.
And that perfectly sets up the ultimate cliffhanger. How many qubits do we need? It is literally the million-dollar question. As we strive for fault tolerance and stable hardware, the race is on to scale up these systems. Are we going to need thousands? Millions? The ongoing high-stakes race for quantum supremacy is happening right now, folks. And as our poet Avayar reminded us at the very beginning, what we've learned so far is just a handful of sand. The rest of the quantum world is out there, just waiting to be discovered. So what do you think we'll uncover next? Thanks for joining me on this explainer, and keep exploring.